The Dynamic Host Configuration Protocol, DHCP, is a network management protocol used to dynamically assign IP addresses and network configuration parameters to devices on a network. It reduces the administrative burden of manually configuring IP addresses and ensures devices receive correct networking settings automatically. DHCP is defined in RFC 2131 and operates using a client-server model, where this DHCP server assigns IP addresses and network parameters to client devices. It typically runs over UDP using two ports: UDP port 67 used by the DHCP server to receive requests from clients, and UDP port 68 used by the DHCP client to send requests and receive responses from the server. Why DHCP is so important, you may ask here. So without DHCP, administrators will need to manually configure each device's network settings, which is cumbersome and prone to errors. So DHCP automates this process, ensuring seamless IP address allocation and minimizing IP conflicts. DHCP operates in a four-step process known as DORA: discover, offer, request, and acknowledge. Discover: the client sends a broadcast message to find available DHCP servers. Offer: the DHCP server responds with an available IP address and configuration details. Request: the client requests the offered IP address from the DHCP server. And lastly, acknowledge: the DHCP server confirms and assigns the IP address to the client. And this dynamic process ensures efficient network address allocation and reduces IP conflicts. The DHCP packet structure is based on the BOOTP protocol and consists of multiple fields that facilitate IP address assignment and network configuration. Now I will explain the DHCP header fields. At first we have the opcode, which is 1 byte, specifies whether the message is a request. If it's a request, it will be 1, or reply. If a reply, it will be 2. Hardware type, 1 byte, identifies the type of hardware, for example, Ethernet, WLAN, or so on. Hardware length, it's also 1 byte. This is the length of the hardware address. It's also called MAC address length. We have hops, which is 1 byte. This is used by relay agents to control packet forwarding. Transaction ID, it's a 4 byte unique identifier for the DHCP transaction. Seconds elapsed, this is a 2 byte. This is the time since the client started the DHCP request. We also have the flags, which is 2 bytes, controls whether the response is a broadcast or unicast. We have the client IP address, which is 4 byte. This is the IP address of the client, if already assigned. Here we have your IP address. This is it's also 4 byte. The IP address of the assigned to the client. This is the new IP address assigned to the client. We have the server IP address. It's also 4 byte. The IP address of the DHCP server. Gateway IP address. This is the gateway or router IP address. We have the client hardware address. This is the MAC address of the client. We have server name. We can also call the server host name. This is 64 byte. And the name of the DHCP server. And it's optional, so it's not mandatory in most cases. We have the boot file. It's 128 bytes. This is the file location for network booting. This is also optional. And now we have the options, which is variable length, and like additional DHCP options like lease time, DNS servers, and so on. And the DHCP also has some message types here. Here you can see this message and use cases. So DHCP Discover sent by the client to locate available DHCP servers and so on and so forth. That will be useful when we will do practical DHCP packet analysis. So I will leave it there, so you can check here to see the DHCP message and their use cases. All right, enough with the theory. Let's get hands-on with DHCP traffic analysis in Wireshark. So dynamic host configuration protocol packets are generated when a device needs to obtain or renew an IP address. And this typically happens in this 4 scenarios. Like when a device first connects to network, so when you turn on a laptop or phone and join to Wi-Fi network, or when an IP lease expires and the client must renew it from the DHCP server, or when manually requesting a new IP address, such as using ipconfig release followed by the ipconfig renew on Windows, which we will do in Windows machine. And for the Linux, you can move between different Wi-Fi networks or connecting a new Ethernet cable, but there's 2 ways to do that in the command line, which I will show you as well. So let's start Wireshark. So we will open a Wireshark to generate DHCP traffic. We will use this Windows 11 machine that is on the same local network as our Linux machine, which is running Wireshark. Now we will start Wireshark and begin capturing on our active network interface card. It might be a Wi-Fi or Ethernet. And to isolate the DHCP traffic, we will use the Wireshark filter here. We will write DHCP, and here we are. Or you can also use the boot P. So this boot P, since DHCP is based on an older boot P protocol, filtering boot P will also show the DHCP packets. But why just if we can do the DHCP, we will do the DHCP as well. And yeah, now we will go to our Windows machine. But I wanted to like show these machines side by side. Okay, that's I think good enough. Yep. Now what we will do here is we will open our Windows machine. Let's actually close the alt prompt. You can see we have 0 packets now. On the Windows machine, we will open the CMD. You can run it as an administrator, but running it with normal user privileges will be fine. So we will use ipconfig release. This command releases the current IP address, forcing the system to disconnect from the network temporarily. Here we are. And ipconfig, you can see we do not have internet right now. ipconfig renew will give us internet access like this, and you can see we have generated some DHCP packets here. So we can also do this kind of thing in Linux as well. So let's actually hide the window since we got the packages. Now we will do the same with our own machine. Here, let's open the terminal. So we will use NMCLI. This is for network manager-based systems. So most modern Linux distributions like Ubuntu, Fedora, Debian, or Arch use this network manager. So you can use NMCLI to refresh your DHCP release. We will release the current IP like we did in our Windows machine. NMCLI device disconnect, and we will enter our network interface card name. So here you can see device successfully disconnected. We do not have the Ethernet access now. Now, what we will do is check our network interface with NMCLI device status. You can see it's disconnected. And what we will do here is NMCLI device connect NS33. This will trigger a DHCP Discover packet, just like ipconfig renew in Windows. And here we have connected to internet, and that's it. And we also generated some packets here. Let's see on the time lapse here. And yeah, that's the packets that DHCP request and the DHCP acknowledgments. So yeah, as we can see, this is the first packet is a DHCP release message. This is our first DHCP packet as a release, which is part of the IP release process when you run ipconfig release on the Windows machine. Now let's break it down step by step. Now first we have the frame here, frame number 1047. This is the 1047th captured packet in the session. So these packets might be less, but as you know, we have filtered out, so there's a plenty of packets. But now with DHCP, we will only see the DHCP packets here. So yeah, so here this means that this is 1047th packet in this capture session. Size on wire is 342. This is the actual size of the packet transmitted. Captured size is the same, which means Wireshark fully captures this packet without any truncation. Interface ENS33. This packet was captured on this Ethernet interface. Yeah, we also, like we did all with our packets, we have the source MAC address, destination MAC address. This is the destination MAC address is likely the DHCP server or router handling the request, and in this here IP version 4, we have the source and destination. Source, this is the Windows client that is releasing its assigned IP, and the destination is a DHCP server, likely a router or switch receiving the release request. And we also have the user datagram protocol UDP header. This is a layer 4, which is transport layer. By the way, this IP version 4 header was layer 3, which is network layer. So here we have in this user datagram protocol, we have source port and destination port. Like I explained in previous lecture, the DHCP has 2 ports assigned to this. Source port is 68 because the client's port for DHCP communication, and destination port is 67. This is the DHCP service port listening for request. So this confirms this DHCP related message, obviously. And also we have the DHCP release. That's the main part of this lecture. And here we can see that the dynamic host configuration protocol, it is layer 7 application layer. So yeah, we have dynamic host configuration protocol release. This is a DHCP release message, meaning the client is informing the DHCP server that it is giving up its assigned IP address. And at bottom we have the message type boot request. So even though this is a DHCP release, it is categorized as a boot request because DHCP was originally based on bootp protocol. If you're wondering what bootp protocol is, by the way, we didn't stop the packet capture, so better we stop it because it's almost packet 3000 packets. So bootp protocol. So you can also get information on Wikipedia with these protocols as well. There's so many protocols. And yeah, so we got this boot request because, as I said, DHCP was originally based on the bootp protocol. Hardware type and hardware address confirms that this is a Ethernet-based DHCP exchange. Hops 0. The packet has not been forwarded through any routers, which is expected in a local area network environment. Transaction ID. There's a unique transaction ID is used to track DHCP sessions. Seconds elapsed. The request was sent immediately without delays. And here we have good old bootp flags. Now we have the broadcast flag is unicast. This means DHCP release is sent as a direct unicast to the DHCP server instead of broadcast. And here we have the client IP address. The client is giving up its IP address, so it sets this field to 0.0.0.0. We also have all the IP addresses is 0.0. So no IP addresses are assigned in this field since this is a release operation. So that's it. So don't confuse with this showing 0.0. This is what release usually does. We also have the client MAC address. This is a MAC address of the Windows machine releasing the IP. We have the magic cookie, DHCP. This field is always present in DHCP packets to identify them as a DHCP packet messages. So server host name not given, boot file not given. Yep. And we also have the options, DHCP options. Option 53, DHCP message type release. This confirms that this is a DHCP release message. It's a type 7. We also have the option 61 client identifier. This includes the client's MAC address, which is used to identify the client releasing the lease. You can see here. And option 255 and end. This marks the end of the DHCP option. And you can see this weird zeros here, lots of zeros. So this means padding is present. So this is a padding basically. And we see the padding to align the packet size. It has no functional purpose, but it ensures proper structure. So when we go to final analysis, this is the DHCP release packet. The DHCP release packet, meaning the Windows client is giving up its IP address. And it was sent directly unicast to the DHCP server at this IP address. And this packet confirms that client's MAC address and includes a DHCP release message, which is at type 7. You see here. And the client has now given up its lease, making this IP available for other devices on the network. And now that we have explained this, the first packet, DHCP release, now let's move on to the second packet, which is DHCP Discover. After we run the ipconfig release, the Windows machine gave up its IP address here and leaving it without an invalid IP list. So at that phase, we did not have any connectivity with the internet. And then after we entered ipconfig renew after like 12 seconds, you can see here, the client needed to request a new IP address from the DHCP server, and this is where DHCP Discover comes in. So now let's open our packet and see what's going on there. Now that we have analyzed the DHCP release, this is the first packet, let's move on to DHCP Discover packet. This packet is sent by the client after releasing its IP address to request a new lease from the DHCP server. Now we first have frame information. You know about this as well, but we will just quickly explain this. I know we have explained this a lot of times. Now frame number 1117, this is the 1117th packet captured. Size on wire is the same as captured size, which means Wireshark fully captured this packet. Interface ENS33. We have the Ethernet to the source MAC address. This is the MAC address of the Windows client requesting an IP. Destination MAC address. This packet is sent as a broadcast to all devices on the network. And we also have the Internet Protocol version 4 header, which is layer 3 network layer. Source IP address 0.0.0.0. The client does not yet have an IP. Destination IP address 255, 255, 255, 255. The packet is sent to all devices on the network, which is a broadcast message. We also have the user datagram protocol. It has a source port of 68, the client's port for DHCP communication, destination port of 67, the DHCP server's listening port. This confirms that obviously there's a DHCP request. We have the dynamic host configuration protocol Discover. So this is a layer 7 application layer. Now, what you see here, this is the DHCP Discover packet, meaning the client is broadcasting a request for a DHCP server to assign an IP address. Now we have the message type boot request 1. Even though it's a DHCP Discover, it is still categorized as boot request here because DHCP is based on the older boot P protocol. And we also have the hardware type Ethernet, confirms this packet is Ethernet based, 0 hops. This packet has not passed through any routers as it's broadcast within the local area network. The transaction ID uniquely identifies DHCP request and will be used to track the process. Second to last, 0, the request was sent immediately without any delay. And we have the boot P flags here. In this case, it's unicast. This means that the client prefers a direct unicast response instead of broadcast. Client IP address, again, 0000. Since the client does not have an IP, this remains 0.0.0.0 for now. So these fields remain 0.0.0.0 as well, since this is just a discovery message and no server has responded yet, which will respond in the next packet actually. We have the client MAC address. This is the MAC address of the Windows machine requesting an IP address. And we also have the magic cookie. You can see here it's a DHCP. So this field is always present in DHCP packets to identify them as a DHCP messages. We have the DHCP options. We have a lot of options compared to previous packets you see here, which is normal. So here we have the message type. This confirms that this is a DHCP Discover packet. Client identifier identifies the client using its MAC addresses. Request IP address. The client is requesting its previous IP address. In this case, it's this. If the DHCP server still has this IP available, it might offer the same one. That's very interesting actually, because it will not confuse the other DNS servers and other users in the same local area network as well. That's actually good, very good. And we also again have the, let's see, requested IP address. So this client is requesting its previous IP address, obviously. So if this will probably be available in this case, but there might be cases like when it releases this IP address, when Windows machine releases, and so some new Android phone comes to network and gets this IP address, then DHCP will give another IP address to this. That's why DHCP is very good compared to using static IPs. And the host name we have here, host name length is 6. Host name is Typhoon. So my Windows machine name was Typhoon. We have vendor class identifier. This identifies that the client is running Windows operating system. MSFT 5.0 is actually meaning Windows. We have the parameter request list. So this client is requesting specific DHCP options from the server, including like subnet mask, router, which is default gateway, DNS server, domain name, static root, net bias information and settings, and some private and classless static root options, which is used by the Microsoft systems. So these parameters tell the DHCP server which setting the client wants included in the DHCP offer response. And here we have the end, marks the end of the DHCP options. So this is the DHCP Discovery packet, meaning the Windows client is searching for available DHCP servers. The client is broadcasting this request to all devices on the network. In this case, it has the 455.455. So this packet contains a request for an IP lease, a preferred IP address, which it had before leasing, a list of requested network settings, including like subnet mask, router, DNS, and more, and the client's MAC address for identification. After this DHCP Discover packet, we will have the DHCP offer packet, which again we will explain. Now let's open the third packet and let's give it a quick look here. And here we have a lot of information here, don't we? Let's actually start from here. So here you can see the frame number, 342 bytes and 342 bytes captured, meaning Wireshark will capture this packet again. Interface. This is a physical layer. We have the data link layer. This is source MAC address. So this is the DHCP server MAC address. Destination is the Windows client that requested an IP. So unlike the DHCP Discover, this packet is sent as a unicast to the client's MAC address instead of broadcasting. We have the layer 3 network layer in the Internet Protocol version 4. Source IP address is the DHCP server's IP address. Destination IP address, the proposed IP for the client. And this confirms that server is offering the requested IP. So they are not fighting over IP here. And we have the user datagram protocol, source port, the DHCP server's port for sending responses, and client's port for receiving DHCP responses. And that's what is important here is DHCP host configuration protocol. So DHCP server is offering an available IP address to the client. We have the message type boot reply to. Since this is a response from the DHCP server, it is categorized as a boot reply. Ethernet address length 6. This confirms that packet is based in Ethernet. Hops 0. This packet has not passed through any routers, since this is a local area network packet. Transaction ID matches the one in the DHCP discovery, confirming that this is a response to the original request. You can see. And seconds elapsed, 0, the response was sent immediately. We have the boot P flags. 0x0000 means it's a unicast. So unlike the discover packet, this offer packet is sent as a direct unicast to the client. In this case, your client IP address is assigned. This is the IP address being offered to the client. And here, since the client does not yet have an IP, this remains 0.0.0, and after that your client IP address shows us. Now the next server IP address is refers to the DHCP server itself, relay agent here, and client MAC address. This is the MAC address of the Windows machine receiving the offer. The client hardware address padding is 0. We have the magic quickie like we did in previous packet. It is this field is always present in the DHCP packets. Now we have the DHCP options here. Look at this. So this confirms that this is a DHCP offer packet. We have the server identifier. DHCP server's IP address here is ending with 254. IP address lease time. The offered IP lease duration is 30 minutes. So the client must renew the lease before this time expires. We have the subnet mask. The subnet mask for the assigned IP. We have router, or default. We can also call that default gateway. Length is 4, and the default gateway is this IP address. Domain name server, again, domain name server is assigned to the client. It resides in the router. Domain name is local domain. NetBIOS TCP IP name server is again it's a router. NetBIOS name resolution services. And at the end we have the options. This marks the end of the DHCP options. So what does this packet represent here? So this is a DHCP offer packet, meaning the DHCP server is responding to the client discover request. The DHCP server offers the IP address ending with 131, which matches what the client requested, so they are not fighting over the IP address. And this packet contains important DHCP options, including like the lease time, subnet mask, default gateway, DNS server. And unlike the discovery packet, which was a broadcast, the software packet sent as a unicast to the client. So what happens next is, after receiving this DHCP offer, the client must now confirm its choice by sending a DHCP request packet. And here we are, DHCP request packet. So the client sends the DHCP request to formally accept the offered IP, and that's how it looks like. Now let's open the request packet, and here we are. Let's make the hex tab a little bit smaller. And now that we have seen the DHCP offer, which is the previous packet, let's analyze the DHCP request. This packet is the client's confirmation that it accepts the IP address offered by the DHCP server. The frame 1, this is the frame number. So here as well, the Wireshark has fully captured this packet, because the size on wire and captured size is same. And interface is our network interface. This is a physical layer, which is layer 1 and the OS side layer. We have the Ethernet header. This is a layer 2 data link layer. We have the source MAC address. This is the Windows client requesting to use this IP address. And destination, this packet is broadcasted to the entire network. And unlike the offer packet, which was unicast, the request packet is broadcast so that other DHCP servers, if any, can withdraw their offers. The type is IP version 4 header, IP protocol version 4. This is a layer 3 network layer. Source IP address 0.0.0.0. Destination is broadcast, so the packet is broadcasted to all devices on the network, and the client does not have an IP address yet. And we have the user datagram protocol 68 as a source port. This client's port for DHCP communication, and destination port 67, the DHCP server's port for requesting for receiving requests. So this confirms it is a DHCP request message. And we also have the dynamic host configuration protocol request. So here the DHCP client is formally requesting the IP address offered by the server, which is request here. Message type boot request 1. Since this is a client to server request, it is categorized as a boot request. Hardware type Ethernet again, confirms the packet is Ethernet based. Hops 0, the packet has not yet passed through any routers. Transaction ID, so this transaction ID matches the one in this DHCP offer, so confirming that this is a response to the server's offer. And second elapsed, the request was sent immediately. Yeah, we also have the boot P flags again. This is a unicast. Even though the packet is broadcasted, the flag suggests the client prefers unicast communication for future DHCP traffic, which makes sense. And client IP address 0.0.0.0. Since the client does not have an IP address yet, this remains same. And these fields remain 0.0.0 because the client is still waiting for final confirmation. The client MAC address here is the address of the Windows machine requesting the IP address. And magic cookie DHCP is always present in DHCP packets. Yeah, we have also the DHCP options. Let's actually make it here. Yeah. I want to see all of this. Yeah. Here we have the DHCP message type. It's a request, length 1, DHCP request 3. Confirms that this is a DHCP request packet. Client identifier length 7, hardware type Ethernet, and client MAC address. Identifies the client using its MAC address, and it here requesting IP address. The client is requesting the same IP address that was offered by the DHCP server, so they are not fighting over the IP address. So this confirms that the client accepts the DHCP service offer. DHCP server identifier, the client specifies which DHCP server it is accepting the offer from. So if multiple DHCP servers had sent offers, this tells the other servers to withdraw their offers as well. Hostname, again, Typhoon. The client's hostname, in this case Windows hostname, is Typhoon. Client fully qualified domain name, again it's Typhoon. The client, this option also allows the client to register its name in DNS. Let's see the flags here. Vendor class identifier identifies the client is running this Windows operating system, MSFT 5.0. up here, Microsoft Net 5.0. And we also have some parameters request list. The length is 14. The client requests network settings here. This is a request thing. So after this packet. So here the client here requests like subnet mask, router, DNS domain name, server, perform router discovery, vendor specific information, net bias settings, private classes static root options, which is used by Microsoft systems. So these parameters tell the DHCP server which setting the client wants to included in the DHCP acknowledgement response. And here we are, the end. So this is a DHCP request packet, meaning the client is formally accepting the offered IP address, in this case ending with 131. The client broadcasting this request to ensure all DHCP servers know which offer is accepted. And the packet contains request for the specific IP, the identifier of the DHCP server, and a list of requested network settings, including subnet mask, router, DNS, and more. And the client's MAC address ending with BF for identification. And after receiving the DHCP request, the DHCP server must now confirm the lease by sending a DHCP acknowledgement packet, which we can see here. So this is the last packet of this communication. This two packet actually belongs to this Linux machine that when we did this disconnect and then connect. So this is the last packet of our Windows communication in DHCP packet with this Windows communication here. So let's open it and see what's inside. Minimize the hex tab. And here we have the more information that we have here. And now that we have seen a DHCP request, the final step in the DHCP process is a DHCP acknowledgement, which you can see. This is the last packet here. So this packet is sent by the DHCP server to confirm that the client has been successfully assigned the IP lease. Now let's open this and see at this information. Packet 1123. Frame number, as well as same Wireshark fully capture this packet. Ethernet layer 2 data link layer, source MAC address. This is the DHCP server MAC address. Destination MAC address. This is the Windows client that requested the IP. So this is the acknowledgement that's coming from DHCP server to the Windows machine. We also have Internet Protocol version 4, which is layer 3 network layer, source IP address. This is the DHCP server's IP address, and the destination IP address. This is the client's newly assigned IP that confirms that lease has been successfully granted. So now our client has this IP address here. UDP layer, which is layer 4 transport layer, source port, DHCP server's port for sending responses, and this destination port 68 here, the client's port for receiving DHCP responses. This confirms that it is a DHCP acknowledgement message. And the dynamic host configuration protocol acknowledgement ACK. Now, the DHCP server is officially confirming that lease of the IP address. And we have some of the packets here, information. So message type boot reply, since this is a response from the DHCP server, it is categorized as a boot reply. This confirms that packet is Ethernet based, 0 hops, so the packet has not passed through any routers. So transaction ID is the same, which matches the one in the previous DHCP packets you can see here. So confirming that this is a response to the client's request. Seconds elapsed 0 again. And we also have the boot p flags again. This is a unicast. The DHCP acknowledgement is sent as a unicast to the client confirming its lease. Client IP address 0.0.0.0, since the client already knows its assigned IP address. This remains 0.0.0. Your client IP address, this confirmed IP address assigned to the client ending with 131. Next server IP address and relay agent IP address. This next server IP refers to the DHCP server itself. And client MAC address, the MAC address of the Windows machine receiving this IP address, IP lease. And client hardware padding, server host name not given, boot file not given, and magic cookie. As we always do, we have this magic cookie DHCP. So this field is always present in the DHCP packets. We have the DHCP options. Here we are. Let's actually scroll it down. We have the DHCP message type. Acknowledgement confirms that this is a DHCP acknowledgement packet. Server identifier here is this. This here shows the length and DHCP server identifier. This is the IP address of the DHCP server basically. Lease time 30 minutes. The assigned lease duration is 30 minutes. The client must renew the lease before it expires. Subnet mask. This is the subnet mask for assigned IP address. So yeah, we also have the router. This is the default gateway for the router. Domain name server. Again, this is the same IP as router because DNS is residing in router as well as NetBIOS. And this is a NetBIOS name resolution service basically. And here we are. We mark the end of the DHCP options. So final analysis is the final packet that after this packet, the lecture will end. So this is a DHCP acknowledgement packet, meaning DHCP server has officially confirmed the lease of IP address that ends with 131 to the client. So the DHCP server unicast the acknowledgement response to the client. So this packet contains the confirmed IP address, which it ends with 131, the lease duration, which is 30 minutes, subnet mask, default gateway, DNS server settings, and so on and so forth, and the server identifier, which ends with 254. And that's basically it. The DHCP handshake is now finished, and the Windows client can start using its assigned IP address. The client will now use this IP until it expires or manually released. So before expiration, the client will attempt to renew the lease. So we can capture this renewal process separately. And would you like to analyze the DHCP lease renewal next, or should we move on to different protocol? But I think if we move on to different protocol, it will be better since we almost covered all of the features, all of the packets of the DHCP here. Thank you for watching for this like almost 1 hour video lecture. I'm waiting you in next lecture. I'm Typhoon.